Vous avez fini le qui 2 ou on n'avait pas fini le qui 2? Bonjour à ceux qui sont en Zoom, désolé pour le retard, désolé tout le monde. So, yeah, please tell me where we got up to. We finished the chi-squared, or we were going to start the chi-squared? Ah, okay. Let me just have a look. Ah, can you hear me on Zoom? Can you hear me?
Yes.
Can you hear me on Zoom?
Yes, we can hear you.
Ah, I can't hear you. Alors, qu'est-ce que j'ai fait encore? A ver. Hi, can you still hear me? And could you say something?
Yes.
So that I can. Can someone speak so that I know whether I can hear
Yes,
you?
we can hear you well.
I can't hear you, so that's a shame. Can you? Could someone try again, please?
We can hear you.
Oh, good, I can hear
We
you.
can hear you.
Yeah, okay, thank you. I can hear you too. I could see if you could hear me well. Right, so, no one can remember whether or not I finished chi-squared, so that's a bit of a shame. And I'm doing several courses at once, so. Chi-squared, yes, no?
I don't think it's finished.
But we started it?
Yes, but very quickly.
Okay, yeah. Okay, yeah, okay. Well, let's go back to chi-squared then. And we'll see how far we get. How many sessions do we have left? Going. Today. I think we have 3 lecture sessions left, and then you will have practical. Yeah, okay, so that's good.
Et sur le truc. D'abord, on a télé et retour à la suite du votre travail. Parce qu'après, on a appris la suite de votre travail.
Évaluation.
Déjà, en fait, c'est parce qu'on est, enfin, le fond, on est plus cher. Ah oui, non.
Did I show you this? Right, we go. Ouais, je vais dessus. Right, hopefully everyone can see all that, otherwise shout out. So, just a recap of where we're at. You remember we talked about the fact that in order to choose the test that we want to use, we have to decide which type of data we have. So either continuous data, quantitative data, or qualitative data. So nominal, whereas the other continuous means numerical data. So we spent some time talking about the tests that look at means in the 1 sample and 2 sample cases with independent and paired data samples. We talked about the comparison of variance tests, didn't we? Yes? Yes. And in the case of 2 samples, and now we are going to look at what happens when we have qualitative data. So the tests of association, about around here. And we saw that in all the cases when we look at the association between 2 qualitative variables, we are going to be using the chi-square test. So, we'll go back to the slides on the chi-square test. So the same steps as usual. Oh, I'm not on the right one. Yeah, so what I said, since I can't remember where we got to in this lecture, we'll just start from the beginning. So just to recap that the chi-square test can be used in lots of different scenarios. We always use it to study the link between 2 qualitative variables. Just a reminder that a qualitative variable can be dichotomous, so only 2 possible categories, so such as open, closed, yes, no, on, off, ill or not, etc. And so when we have a dichotomous variable, then knowing the frequency of one of the variables is sufficient to describe the whole distribution of the variable. Whereas if you have more than two categories, then you have to give the frequency of each category in order to describe the distribution of the variable. I remember we talked about blood groups and etc., didn't we? Yeah? So I think we must have got at least to the first part. So anyway, the chi-squared test can be used either to compare a frequency or a distribution to a theoretical value or distribution, or to compare several distributions. And the names of the test differ depending on the question. You can call it a conformity test when you're trying to see whether the distribution fits a reference distribution, or you can call it an independence test when you're trying to decide whether two variables are linked by a relationship, have a relationship. And then in those cases, it's called an independence test, because the null hypothesis will be that there is no relationship between the two variables, so the variables are independent. Whereas if we do not reject the null hypothesis, if we reject, the null hypothesis, then that means the variables are independent. And then you can also use it to test homogeneity. So thus there are various names given to these tests. Now, when we, the principle of a chi-squared test is the same as other tests: define the null and alternative hypothesis, deduce what is expected under the null hypothesis, and in particular, in the case of the chi-squared test, we need to calculate expected numbers which come from the frequencies. We compare observed and expected numbers, and we conclude by rejecting or not rejecting the null hypothesis. For the chi-squared test, the hypotheses are expressed in terms of frequencies, but we do need the numbers to calculate the test statistic. And usually we do this by using a contingency table, which contains the observed numbers Oij and the expected or calculated numbers Eij. So O for observed, E for expected. So this is what we call a contingency table. So if you imagine two qualitative variables A and B with respectively L and K categories. So variable A has L categories and variable B has K categories. And then we write in this table the number. So we assume we have a sample and we know for each individual what is the value of category variable A and variable B. And here is the number of people in this category who have A1 and B1, etc. So to make it simpler, I was imagining that we could have we could imagine that these are the blood groups. So A, B, and O. So that means there's 4 categories here. And these are different countries, so of origin. So say Albania, Belgium, and Cambodia, okay? Albania, Belgium, and Cambodia, so 3 countries, ABC. And so we have, admit that we have 100 Albanians, 150 Belgians, and 200 Cambodians. And we know their blood groups, so we can say this is the number of people from group A in Albania, number of people of group A in Belgium, etc., number of people group B, etc. Okay, so this is what we call a contingency table. We write all the numbers, calculate the totals. So this is the total number of people in the sample in each country. And this is the total number of people from group A, from all the 3 countries, group B, etc. Okay, so these are the totals. Then we construct the contingency table of the expected number under the null hypothesis. So we haven't said what the null hypothesis is. In the case of 2, as I said earlier, when you look at 2 variables together, you're trying to see whether the distributions are the same in both. The distribution of variable A is the same in each population B, for instance, okay? So the null hypothesis here, what do you think it would be? If we're talking about blood groups and countries, what do you think the null and alternative hypotheses would be? Try and imagine. There's only two, you can just say it, you don't need to say it with equal signs, but just in terms of the distribution, we have blood groups, we have countries. What could the null hypothesis be? We're thinking about how the blood groups are, the distribution of the blood groups. What do you think? That they're all equal, yes. So if you say it in terms of distribution, that the distribution of blood groups is the same in each country. Very good. Okay, that would be the null hypothesis. The distribution of the blood groups is the same in each country. And if we wanted to write that down, that's fine as a null hypothesis. And the alternative hypothesis is that there is a difference in the distribution. So if we wanted to write that down, we would say that means that for that to happen, we need to have the proportion of, if I want to write it down, I hope the camera is working. So someone will have done it up there. Proportion of people from group A in Albania should be equal to what? Should be equal to the proportion of people of blood group A in Belgium, equal to proportion of blood group A in Cambodia, and P of B in Albania equals P of B in Belgium equals P of B in Cambodia, and P of AB in Albania equals P of AB in Belgium equals P of AB in Cambodia, and P of O in Albania. Okay, so that, all that is the null hypothesis. Okay, that would be how you would write it down. But of course, even in an exam or whatever, it is valid to just say the distribution of blood groups is the same in all three countries, okay? That's the same as saying that. And then the alternative hypothesis is just at least, or either there is a difference in the distribution, or you could say at least one of the equalities above is false, okay? Because if you have one which is different, then everything else is going to be imbalanced, okay? So that is our null hypothesis. So now if we go back to this expected, so we have the observed numbers and we're looking for the expected numbers. So how do we find the expected numbers? So first you have to see that in this contingency table, the totals here are the same as in the observed table, okay? Here, we calculated the total number in each country and the total number in each blood group, and there's a grand total. And in this table, we leave the same totals, okay? So that's important. The totals are the same. And we want to know what is the expected number of people of blood group A in country in Albania if the distribution is the same. So what we need is a kind of theoretical distribution of proportion of people with blood group A. So what we're going to do is we're going to take the total of people with blood group A and divide it by the grand total, and that will be a kind of expected proportion, okay? And then because we have 100 in Albania, 150 in Belgium, and 200 in Cambodia, we're just going to multiply A1 over N by B1 to find the expected number here, okay? And then A1 over N times B2 to find the expected number here. A1 over N times B3 to find the expected number here. Do you agree? But if we had 200 people in each country, then we would find the same expected number, wouldn't we? But because we want it to be the proportion, which is the same, it means that the expected numbers will be different, but the proportion in each country is equal. That is under the null hypothesis. Yeah, do you understand that? Is that okay for everyone? So the expected number, so this is the explanation of where this comes from, but if you didn't quite understand where it comes from, you can just use the formula, which is A for each square, the expected number, each place in the table, the expected number is AI over N multiplied by BJ, okay? So if I'm looking for EIJ, I do AI over N multiplied by BJ, the end of the line times the end of the column divided by N. Is that okay? So that is, if the null hypothesis is true, then I can calculate all the expected numbers under the null hypothesis. And then what am I going to do? I'm going to compare my numbers with my expected numbers for each of the table cells. The cell, ça veut dire la case du tableau, d'accord? Pas la cellule, on n'est pas en bio, hein? Okay, each table cell, that means each square in the table. And if the null hypothesis is true, then we expect there to be not the difference between OIJ and EIJ should be close to zero, okay? If the null hypothesis is true, then we should have almost the same as the value we expected. And so the test statistic in the case of the chi-squared test is the sum of the square of this difference over all the cells of the contingency table. So it's the sum, the test statistic is the sum of OIJ minus EIJ squared over EIJ for all the cells in the table, okay? And so we want this difference, you can show that the difference for each cell tends towards a standard normal distribution, which means that the sum of all those differences, squared differences over EIJ tends towards the chi-squared distribution, hence the name of the test, chi-squared test. So the chi-squared test tests whether the test statistic based on these differences is no greater than a certain threshold. So the same as in other tests. So this is the test statistic, sum over all the columns and all the lines of OIJ minus EIJ squared over EIJ. Under the null hypothesis, this follows a chi-squared distribution with L minus 1, K minus 1 degrees of freedom for any integers L and K greater than or equal to 2. And we reject the null hypothesis if this calculated test statistic is greater than a certain threshold, which we can find in the table. And the assumptions for chi-squared is not that the distribution is normal or anything like that. It's just that the expected numbers, and be careful, you can circle that in red, it's only the expected numbers that have to be greater than or equal than 5, not the observed numbers, okay? So only the expectant numbers have to be greater than or equal than 5, not the observed numbers. So if we look at this example, so I did it here, except that I said AB, ABO, and the countries, but it doesn't matter, it gives the same results. So collecting data concerning blood groups AB, AB, and O of 3 samples of adult women, so I chose 300 countries, Iceland, Mali, and Vanuatu. The numbers are observed are given below, okay? So we want to know whether the distribution of the blood groups is the same, whatever the geographical region of origin at the 1% significance level. So could you calculate, so how many times how many expected numbers do we have to calculate here? Are these the observed or the expected numbers? What do you think? Observed, yeah. These are the observed numbers, it says it here. And we need to calculate the expected numbers to do the chi-squared test, okay? So using what I said before, could you calculate the expected numbers of at least 4 of the squares, okay? And so you need to use the formula that I gave before, which is AI times BJ divided by N to get the expected numbers, okay? And then, so just as a note, often expected numbers, they might not be exact. So you can use, for expected numbers, You can have a value like 30.8, even if it's talking about numbers. You can leave a comma, leave a decimal point, okay? So you do the calculations for four cells, whichever ones you want. Calculate the expected numbers, okay? Did we do how to check whether a distribution is normal or not? No. Not. Sorry?
No, we did not do it.
Okay, thank you. I'm doing similar lectures in different courses. Comment vous avez trouvé? Did you find the expected number? You found a few? So, what expected number do you here for A? What did you find? How do you find the expected number here? Can you tell me what the calculation is, please? Here?
132
Yeah.
times 125 and 335.
Over, yeah. I said under, but yeah, good, yeah, over. Okay, so, yeah, everyone agrees, so that means that you should have found 49.3, and everyone can check whether the ones they calculated are correct, okay? So, here are examples, and just before that, you can double check that the null hypothesis is what I said earlier. The real, if Pij are the real percentages of women in each blood group type in the three populations from which the samples are drawn, these are the real proportions, and they have to be equal for A, B, and O in each population. And the alternative hypothesis is that at least one of the equalities is false. And so here we have the expected numbers, and now we have to check whether all the expected numbers are greater than or equal to 5, which is the case here. So we can proceed with the calculation. Now, how many terms will we have in this sum to calculate the test statistic? How many, a term of a sum, le terme d'une somme? Combien il y en a? Can you tell me how many terms we have? What do we have to do to calculate the chi-squared? We have to do, okay, so 54 minus 49.3 squared over 49.3 plus minus 23.1 squared over 23.1 plus So there are 12 terms in this sum, okay? You have to sum it over the 3 lines and the 4 columns. And so if you do that, you find the observed value of the test statistic, 22.56. And then we have to compare that with the threshold value for a chi-squared distribution with k minus 1, L minus 1 degrees of freedom. So that means the number of categories minus 1, so 4 minus 1 is 3, times this number of categories, 3 minus 1 is 2, so it's 3 times 2 is 6 degrees of freedom, okay? And we have to find this value in the table. So one very important thing is that, do you remember how I explained that when we have a unilateral alternative hypothesis, we have to use this table. When we have a bilateral, we divide by 2. Do you remember that? But for the chi-squared, so you have to write that in red as well. Chi-squared test, you just consider the values in the table because we can't have unilateral, bilateral, and chi-squared, okay? It's just a different, because it's a different type of test. So we will just always use the value in the table as if it was a unilateral alternative hypothesis, okay? So here you can see that 6 degrees of freedom is this line. And for a 1% significance level, because that's what it said in the initial question, at the 1% significance level, is the distribution the same? So at the 1% significance level, the threshold value is 16.81, okay? So we found 22.56, the threshold is 16.81, so we reject the null hypothesis because this observed value is greater than the threshold value. So it means that there's too much difference between the observed and the expected values. We are beyond what we expect. So this means we reject the null hypothesis that the distribution of the blood groups is the same. So this means there is a significant relationship between the distribution of blood groups and the geographical origin in these 3 populations.
Madame, je
Oui.
comprends pas. Qu'est-ce que ça veut dire quand on dit que le E il est supérieur et égal à 5?
Ça, it doesn't mean anything, ça veut rien dire, mais c'est juste une condition d'application. C'est-à-dire, on ne peut pas utiliser le test du qui 2 si, comme dans les autres cas où on dit il faut que la distribution soit normale ou il faut que les variances soient égales, d'accord? C'est juste une condition. It's just a condition. For the chi-squared test, you have to check that the expected numbers are greater than or equal to 5 so that you can do the test, okay? So, and here is the output. You can see that the p-value is equal to 0.001. And so, the p-value is less than alpha, 0.01, okay? Here, p is equal to 0.001, which is less than alpha equals 0.01. So we reject the null hypothesis, which is the same conclusion. Okay, remember there's always two ways of concluding concerning tests. Right, so what do we do? This was following your question. What do we do when the expected numbers are less than 3? Okay. What do we do when the expected numbers are less than 5? Sorry, we can use another test called Fisher's exact test, but I'm not going to show you how you calculate it. You have to use the software to calculate it. And so, because it looks at all possible combinations of the table, and this test gives results which are close to the chi-square. So, is that okay concerning the chi-squared test? Do you understand the principle of the chi-squared test? Yes? Now, do you have any other questions concerning chi-squared test? So what we could do is, I'll just do a couple more examples. I don't think I translated them into English, but I will say it orally. So, imagine, I'm going to give you another example to see if you can calculate it. So why don't you think about this example? I will say it in English, so those who don't understand French, please listen carefully. So we imagine you have a population of workers, and you check whether or not they were non-smokers in the past 15 years and whether or not they had lung cancer in the same period, okay? So there are 492 non-smokers, and we suppose that they are either non-smokers for 15 years or smokers for 15 years, okay? They didn't change their habits over those 15 years. So imagine there are 492 non-smokers, and in that population of of non-smokers, 2 cancers were observed. And there's another group of 531 smokers, and 17 cancers were observed in that top group, okay? So 492 non-smokers, 2 cancers, 531 smokers, 17 lung cancers. Is there a link between smoking and lung cancer at the 1% significance level? So could you construct the contingency table, write down the null and alternative hypothesis, So start by writing down the null and alternative hypothesis. You can either write it using a sentence, une phrase, or you can use it, try and write equal signs, okay? And then you do the contingency table, calculate the test statistic, and go from there, okay? Does anyone on the Zoom need me to translate that again, or is that okay?
It's okay, thank you.
Okay, right. So You finished or not yet? You finished? Yes? Is everyone finished? Can we do the, those? Would someone like to come and tell us what they found for this? Please don't all shout at once. So who would like to come and do it on the board? Yeah? Would you like to come and try and do it, please? Yeah, thank you. So what, you can write the null and the null hypothesis and the authentic. So I will say, I don't know if, oh, okay, I don't even know if the camera is on. Anyway, so, your null hypothesis is no, there is no relationship between smoking and cancer, and the alternative hypothesis is there is a relationship between smoking and cancer. Does everyone agree? Yes? And if we want to write that as a proportion, how could we write it? Yeah?
Que la proportion des malades, enfin des cancéreux qui fument soit égale à la proportion des cancéreux qui ne fument pas.
Ouais, très bien. So you can write that maybe, P de cancer chez les fumeurs, slash fumeurs ou CF, oui, voilà, c'est bien, égale P de cancer chez les non-fumeurs. Ouais, voilà, okay. So that's another way of writing it, and then the alternative hypothesis is that it is different, okay? So here it's easier than in our previous example. So can you now can you write the table, the contingency table? I don't think at the end of the year I will know how to use this thing. Okay, say hello to the camera. I want to go over there.
Normalement, il y a une position que...
Ben ouais, mais ça marche pas très bien. Parce que les positions préenregistrées, elles sont pas. Moi, je veux qu'il aille sur le tableau.
Non, oui, la tour des
À la main, ça marche?
Oui, non, là.
Ouais, avec ça, ouais, mais voilà. Allez, avant. Encore? Je sais pas, des fois, il s'arrête.
Des fois, ça marche pas, il faut passer dans l'autre sens. Faire le tour par l'autre côté.
Right, so that is the contingency table. Does everyone agree with that contingency table? Yes? Okay, and voilà, vous êtes sur la caméra. So that, are those the observed or the expected frequencies? Observed. So now can you give us the expected frequencies? So the expected numbers are 9.9, 9.1, 521.1, and 482.9. Everyone agree? Yeah. So just as an aside, if we had 500 smokers and 500 non-smokers, what would the expected numbers, what would we see as expected numbers? If we had 500 and 500? Well, say it was 9 as an expected number. Do you agree that we would have the same number expected if we had the same totals, we would have the same number expected. So just to say, it's the reason why the expected are different is because the totals are different, okay? Ça vous paraît peut-être évident, mais juste si ici on avait 500 et 500, ben là on aurait exactement le même nombre attendu. Hein, on fait 19 sur 1023 fois 500. Bon, okay. So what did you find? Did you calculate the chi-squared? Yes, what did you find?
10,83.
Right, so it probably depends on how you round the numbers, but okay, 10.9 or something. And you have to remember to check whether the expected are greater than 5, greater than or equal than 5, which is true. And so here we have 4 numbers to sum, 17 minus 9.9 squared over 9.9. And this is the expected number. Oh yeah, and so what do you think the number of degrees of freedom is? 1, okay, because it's 2 minus 1 times 2 minus 1. And so here, if you look in the table, for a 1% significance level, the threshold is 6.63. And so what was your conclusion?
On rejette H0.
Yeah. The null hypothesis is rejected at the 1% significance level because 10.94 is greater than 6.63. So we reject the null hypothesis, and so there is, thank you very much, a relationship between smoking and lung cancer. Is that okay? You do realize that in the 30s, they told people it was good for you to smoke. Yeah, do you know that? In the 30s and 40s, before, now we all know that smoking is bad for you. But in the 30s and 40s, they used to say, oh, it might be good for your cough if you smoke a bit, okay? You can find old advertisements on internet and you'll see. Okay, so that was just another example of a chi-square, so I think you understand the principle. So now we will, and the p-value is 0.001. So right. So we have now talked about the chi-squared test, and when the chi-squared test can't be used, so you see here I wrote the expected I wrote down the number, conditions for the chi-squared test is that the expected numbers are greater than 5, and when you can't use the chi-squared test, you can use Fisher's exactness. So we will see that, you'll see that with Cataline, when you use software to do the test, that if chi-squared test is not applicable, you can use this one. So I just want to come back to, I just want to come back to the fact that for most of these tests, there is an assumption, which is you have to check that the variable is normally distributed. And for the moment, we have just said, okay, suppose the variable is normally distributed. But how do we check that the variable is normally distributed? So we are going to go to the lecture entitled How to Check Whether a Distribution is Normal. And I'm just going to check whether I put it online or not yet. If I haven't, I will do it, of course. Elle y est ou pas? Oui. Okay, donc c'est bon. Right. So, how do we check whether a distribution is normal? This is useful mostly for in statistical testing, because it's a condition for the use of many parametric tests. And we're going to see that there are different methods to check for normality. There are descriptive methods, graphical methods, and numerical methods, i.e. tests. So it will do a quick overview of all the different methods. So why and when do we need to check for normality? Either we just want to check for fits, whether a distribution fits the normal distribution. So we want to check whether an observed distribution fits the theoretical distribution, in this case, the normal distribution. And as I said, it is also the assumption for several parametrical tests, such as the student t-test, Fisher's test, linear regression, which we'll see next, and analysis of variance. So it's important to be able to check whether a distribution follows a normal distribution. Just to remind you that the normal distribution, also called the Laplace-Gauss or just Gauss distribution, is frequently used to describe biological variables, as I said, resulting from a large number of independent phenomena. And it has this distribution density function shape. This is the formula for the normal probability this density function. And we call the mean a mu and the variance sigma squared usually. And why is it so important to check whether we have a normal distribution? It's because the property of the law of large numbers and central limit theorem allows this test to be made without knowing the initial distribution of variables in the case of large samples. So because, so I think we said that before, so I'll go through that. Just to remind you that for any random variable x which follows a normal distribution, approximately 68% of the values of x are within one standard deviation of the mean. Approximately 95% of the values of X are within 2 standard deviations of the mean, and 99.7 are within 3 standard deviations of the mean. So these are important properties of the normal distribution. So there are descriptive methods to check normality using histograms and box plots. And you can also look at distribution characteristics such as skewness and kurtosis. I will explain what that is. So if you just do a histogram of some variable which you have, here I took a concentration, you can get a first impression of whether a distribution is normal. Would you say that that distribution is normal or not? Not? Why not?
À gauche.
Alors, biaisé, oui. En fait, you say biaisé à droite. This where so I mean it's a question of symmetry. So as you saw, it has to be symmetrical, okay? But if we see that this distribution is very long, then we say it's biaisé à droite. Okay, but you got the right idea. So yeah, we can see it's not symmetrical. So the advantage is a very quick overview of the distribution. The disadvantage is that it's very dependent on the width of the intervals. You know, in a histogram, you can decide how wide your intervals are when it's a continuous distribution. And if we made these intervals wider, then we would see a different shape. Okay, the shape would change, so it might change our mind. You can also do a box plot. Remind you that in a box plot, you're looking at the median, the first and the third quartile with interquartile range, and you can see, so this is the same data, the concentration data. You can also spot easily that there is a bias, that there are greater concentrations have more values, and you can see extreme values. So those are 2 quick ways to look at the distribution. You can also actually use numerical parameters called skewness. Skewness looks at the symmetry of the distribution, and the actual calculation is the values of X minus the mean cubed over the standard deviation cubed, and you take the mean of that expectation of that. So for a normal distribution, the skewness is supposed to be 0. And if the skewness is not 0, it means the distribution is biased. So if the skewness is positive, it means it's biased this way. If the skewness is negative, it means it's biased this way. And if the skewness is 0, then the mode, the mean, and the median are equal. And the kurtosis is I think it's a Greek word, and it means how flat the curve is, okay? And so there's also a way of calculating kurtosis, and for a normal distribution, the kurtosis is supposed to be 3. And so using those parameters, you can devise statistical tests to check whether a distribution has a certain skewness and kurtosis. So for instance, with my data, the kurtosis is 6.1, so clearly not 3. Not the shape that we would expect of a normal distribution, and the skewness is positive, which shows there is a bias towards the right. So another graphical method is to superimpose the closest normal distribution on the histogram. And so there you can see quite clearly that there is this side of the distribution which is too high compared to what is expected, and the skew to the right. And there's another graphical method which is called the kernel density plot. Because the histograms are sensitive to the width of the bins, the intervals, if you ask for a smoothed version of the data, so in blue is the same data as the histogram, okay, it's the concentration, and in red is the closest normal distribution. And so there you can see, it says it here, blue is kernel density estimate, and red is normal density, and you can clearly see that the curves are not superimposed, and so there doesn't seem to be, it doesn't seem to have a normal distribution. Another graphical method is, and so I'm giving you different graphical methods. Obviously, I'm never going to ask you, no one does it by hand. You will do it when you have software, and you will be able to check it when you do the le TP, the practical on the software. You will be able to check whether the distribution is normal using these different methods or some of the methods. So this graphical method is called a symmetry plot. And what it does is you plot the distance above the median, okay, for each value of that you're looking at. You look at the median minus each value, and the distance above the median as a function of the distance below the median. And if the variable is symmetrical, then you should have points that go along the line y equals x. And if the points deviate from the line y equals x, this shows that there are more values above the median than below. The distance above the median is greater than the distance below the median. And so it shows that there is asymmetry. And so that's why it's called a symmetry plot. And it shows that the distribution is not normal. Another graphical method is called the normal quantile plot, or Henry's line. And this time you graph the quantiles of the studied variable. So you put the variable in the right order, and you look at the different percentiles, 10th, 11th, etc., as a function of the quantiles of a normal distribution. And these should also align on the line y equals x. And if they don't, if you see that they deviate, especially in the tails of the distribution, this shows that the distribution is not normal. Final graphical method, the normal probability plot, and the same, you're expecting the points to be along the y equals x line, and if they're not, this shows that there is deviation to the normal distribution. So those were 4 graphical methods which are easily enable you to check whether a distribution is normal. And another method is to use statistical tests. So please listen carefully, because here there are lots of different statistical tests which you can use to check whether a distribution is normal. And they have different names, but they're all called normality tests. So depending on the software you use, they will not be the same ones. But for all of them, without exception, the null hypothesis is that the variable has a normal distribution, and the alternative hypothesis is that the variable does not have a normal distribution. So I'm asking you a question. If I have a variable and I do a test for normality, and I find that I reject the null hypothesis, will that mean of one of those tests? Does that mean that the variable has a normal distribution, can be considered to have a normal distribution or not, if I reject the null hypothesis? Can I say the distribution is normal or not? Not normal, okay? So, for instance, here we have a test called Jacques-Bérat, based on the symmetry and the flatness. So it uses the skewness and kurtosis coefficients. The null hypothesis is that the variable has a normal distribution. And this is the test statistic, but I won't ask you to calculate it. So here, if I use if I use this variable and do the test for normality, I find a p-value of 0.0000. So at the 5% significance level, can I say that n roll follows a normal distribution? Yes or no? This is the p-value for the test statistic, the p-value, petit p, for this variable. If that is the null hypothesis, can I say that n roll follows a normal distribution or not? Okay, I'll say it once more. The null hypothesis for all the normality tests is that the variable has a normal distribution. I do the test and I find a p-value of 0.000. You can put a 9 in the end if you like, 0.0009. So will I reject or not the null hypothesis with this p? So you say no, and you say reject.
Yes.
P is less than 0.005. Yes. If the alpha is equal to 5%, and I have P, which is, you can admit it's P equals 0.000. Okay, let's say it's that. So P is less than 0.005. So reject the null hypothesis. So can I say that enroll is a normally distributed or not? No, okay, it's not normally distributed because I'm rejecting the null hypothesis. For the next one, res, can I say that it's normally distributed or not? It is, okay, because I do not reject the null hypothesis. So that means I can consider that the variable is normally distributed, which means that when you are doing a student t-test, and you have to go through the step of checking whether a distribution is normal so that you can do the student t-test, you are going to hope that you do not reject the null hypothesis. You agree? Yes, you're going to hope for a p-value which is greater than 0.05. Is that okay?
Yes.
We just confused the direction, okay? Has everyone understood? Yes? So, so yeah, that was the answer. And then there's another one, same, it's a different test, but same null hypothesis, the variable has a normal distribution, and same variables, so the p-values are slightly different, although that one you can't tell, but you can see that one's slightly different, but same conclusion. So important comments concerning the statistical tests. The advantage of using statistical tests is that when there's a large number of variables to check, you can use tests and you can program something which is automatically will calculate all the tests and tell you whether or not the distributions are normal. But be careful because the tests are strongly influenced by the sample size, okay? So for small samples, they tend to not reject the null hypothesis and tell you that the distribution is okay. For the very large samples, because it's got much more power, it will almost systematically reject the null hypothesis, even when you're only slightly different to a normal distribution, okay? So be careful when you do a statistical test. You should also you should combine graphical and numerical methods and take into account sample size when you interpret the test. So basically, yeah, well, I'll tell you later. So it's important to know that, okay? If you have small samples, then it's probably, or medium samples, it's okay to use the tests. But because with very large samples, you might reject the null hypothesis, it's good to also check whether really you are a long way from the normal distribution or very close. So what do we do when the distribution is not normal? You've checked your distribution, it's not normal. So you could try and transform either you can use non-parametrical tests, okay, that's what I wrote on my thing, or you can transform the variable and see if a transformation of the variable, which means apply a function to it, will come closer to the normal distribution. So for instance, here I have my variable, the raw variable is called enroll, okay, this is my variable, and I'm going to square it, cube it, take the square root, take the log, do 1 over the square root, 1 over the variable, to see whether all its transformations bring me closer to a normal distribution. So here you see, this is the variable. Can you recognize that this is the variable I showed you at the beginning, so the histogram? You recognize that variable? Yeah, the same as before. And here I squared it. Is that more like a normal distribution? Yes or no? Does that look more like a normal distribution than that one? If you look at the histogram, no. If I cube it, is that better? No. Okay, if I take the square root, is that better? Is that more normal? Yes, okay, it's more normal. Log, even better, it's even more symmetrical. 1 over square root, it's better than the other ones, but not as good as the log. The inverse is 1 over the variable, 1 over that is skewed the other way, 1 over the square root, 1 over the cube. So which one would you say is the best approximation to a normal distribution? The log, okay? So if we go back to here, you see, you can look at it visually. And here there's in this software, it doesn't have it in all softwares, it will test different functions. And then it will do a chi-squared test, sort of like the one we've learned, to see how far away your distribution, the one you've calculated here, is from the normal distribution. So if the p-value is very small, it means we're rejecting the null hypothesis, so it's not at all a normal distribution. And here you can see that for this log, we are not rejecting the null hypothesis, so it's close to a normal distribution. See, we look for the transformation corresponding to the smallest chi-squared, which is the distance between the observed values and expected values if the variable follows a normal distribution. So the log is the closest to the normal distribution. So now we could do the test with using log of the variable instead of doing the test using the raw variable. Okay, that's one way of doing it. Or, like I told you right at the beginning, if the hypotheses are not okay, then you can use a non-parametric test. Okay, so there's different ways of doing it. So just to conclude, the take-home points are that when you're trying to check for normality, you can use descriptive methods, graphical methods, and I put the four we talked about, or use numerical methods, i.e. test statistics, where there are lots of different tests, but it's always, remember that the null hypothesis is always that it follows a normal distribution. And so we reject the null, if you reject the null hypothesis, then the distribution of the variable cannot be considered normal. And remember to use a combination of these methods is the best thing to do, because if you use only test, remember that sample size will influence the results of the statistical test. Is that okay? Any questions on checking for normality? No questions? Yeah? Right. Good. Any questions online? Non?
Moi, j'ai une question.
Ah, ok. Faut mettre le cours.
En faisant le log,
Oui.
on est d'accord qu'on peut, enfin, comme on avait tout à l'heure, qu'on peut normaliser les données. Mais
Yeah.
quand on fait l'analyse
Yeah.
et quand on dit est-ce que c'est
Ouais.
significatif ou pas, la différence, je veux dire, entre deux groupes
Yeah.
de mesures, enfin, est-ce que la valeur qui nous dit s'il y a une différence ou pas, il faut le passer à...
No, you don't have to retransform it. So you can do the whole statistic. So for instance, if you wanted to compare, say, the means between two populations, and you have recognized that the variable is not normally distributed, so you need to transform it into log. Then you can do the, for instance, student t-test using log of the variable. You can conclude that the distribution, for instance, in women is the same as the mean of the women is the same as the mean of the men. And you can conclude that the means are equal, even if you have transformed the data. Do you see what I mean? Because you're only using the statistical test to check whether the means are equal.
Oui.
So the fact that you're looking at the log means doesn't matter. It's the statistical test is looking at the logs, but it means that the original data is okay. Does that answer your question? You don't need, when you do the test, once you've decided to use the log of the variable, then you just do the whole test with log of the variable.
Et j'espère que j'ai compris.
Et je peux le dire en français.
Je préfère en français.
Ah, ok, je le dis en français. Donc, si vous décidez qu'il faut transformer les données,
Oui.
et que vous faites log de la variable, ok, vous faites tout le test de student avec log de la variable, vous ne transformez rien au milieu, vous laissez la tête, etc.
Oui.
Et vous faites votre conclusion, et cette conclusion, elle est valable pour log de la variable, mais elle est aussi valable pour la variable brute, si vous voulez. Vous voyez ce que je veux dire? En fait, la transformation, elle vous permet juste d'utiliser le test, mais les conclusions, et d'utiliser le test avec les variables, comme si c'était votre nouvelle variable, y égale log de x.
D'accord, merci.
Okay, so, so now we are going to talk about linear correlations. and linear regression. So. Right, correlation and linear regression. So if we want to go back to the, I'll just show you the other slide first. If we go back to this. So we have now talked about the orange, except ANOVA. We've talked about comparing means, talked about comparing variances. We talked about comparing qualitative data. And now we are going to look at the association of two quantitative variables and talk about correlation and regression. So, if we want to measure the association between two quantitative variables, there are three types of association that we can talk about. There's dependent, monotonic dependence, or concordance. Dependence, two variables are dependent if a measure of the first gives some information on the measure of the other. It can be very general and vague, such as blood, the pH of your blood and the degree of consciousness. If your pH of your blood is too high or too low, you will die, okay? But you don't know exactly what the relationship is. There's just a relationship of dependence. On the other hand, if two variables are dependent in a monotonic manner, then this means that if one variable increases, the other decreases, or if one variable increases, the other always increases. So this is called a monotonic dependence. And an example could be systolic and diastolic blood pressure, where if one increases, the other increases. And finally, concordance is the strongest type of association between two quantitative variables. Two variables are concordant if they lead to the same values. So for instance, if you dose the active substance of a drug using two different techniques, then you expect them to give the same value, exactly the same value, okay? And so you're expecting them to be concordant, not just varying in the same way, but to give the same result. So we will not, but for dependence, there's no measures available to quantify these associations. For monotonic dependence, you can measure this using a correlation coefficient, which we will talk about. And for concordance, you can measure it using an intra-class correlation coefficient and also using descriptive methods, which we will probably mention later on. So correlation and regression are used to quantify the joint variability of two variables. Now, the aims of correlation and regression are to study the association between two quantitative variables, as I said before. So imagine X and Y, waist circumference and BMI, for instance. So BMI is body mass index. Everyone knows what body mass index is, yeah? IMC en français. The question is there an association between waist circumference and BMI? Okay, so if you just want to know, is there an association, then you can use correlation, and you can see that in that case, waist circumference and BMI, X and Y, play symmetrical roles. If you say X is correlated with Y, it's the same as saying Y is correlated with X, okay? So you're just looking at an association. But a different question could be, can we use waist circumference to predict BMI? Okay, that could be a different question. Can I use waist circumference to predict BMI? In that case, you can see that X and Y, even in the sentence, don't play the same role. Okay, dans la phrase, est-ce que je peux utiliser X pour prédire Y? C'est pas la même chose que de dire est-ce que je peux utiliser Y pour prédire X, d'accord? Alors que quand je parle au-dessus de la corrélation, je dis X est corrélé avec Y ou Y est corrélé avec X, c'est symétrique. Et on va voir que en statistique, effectivement, la corrélation, elle est symétrique. Qu'on parle de X ou de Y, ça revient au même. C'est X corrélé avec Y ou Y corrélé avec X, ça donne la même chose. Par contre, dans la régression, et on va voir qu'il y a la régression linéaire, la régression logistique et tout ça, ben, le truc très important à comprendre, c'est que Y et X ne jouent pas les mêmes rôles, okay? So you have to remember that in regression, Y and X do not play the same role because we are trying to predict one as a function of the other. And so in regression, contrary, which is different to in correlation, in regression, we are describing the variations of Y as a function of X. We are trying to predict Y from X, and so that Y and X do not play the same roles and they have different names. So Y is called the dependent variable or the response variable or the outcome, and X is called the independent variable, the explanatory variable, the predictive variable, the covariable. Okay? So this is the big main first difference to understand between correlation and regression, but they are both used when we have two quantitative variables. So now consider the two quantitative variables, for instance, systolic blood pressure and diastolic blood pressure. Before you do any calculation, correlation or regression, you want to examine the data through graphs. So here, if you look at diastolic blood pressure according to systolic blood pressure, you can see that with a scatter plot, so a graph where each pair X and Y is represented by a point, it enables you to observe the shape of the distribution, the direction. So when X increases, does Y increase or decrease? So here, when X increases, Y increases, and you can see whether there are extreme values. So first, we need to define covariance. What is covariance? Covariance quantifies the joint variability of two quantitative variables. So you know about variance, okay? The variance of X is the sum of X minus mu squared over N. And the covariance of X and Y is the sum of X minus the mean of X multiplied by Y minus the mean of Y for each individual going from 1 to n divided by the number of individuals, okay, the number of values. So here, this is the formula for covariance, and you can see that if you look at the covariance between X and itself, X and X instead of X and Y, then you would go back to the variance of X, okay? If X is equal to Y, then it will be X minus mu times X minus mu, so it would be X minus mu squared, and so that's the formula of the variance, okay? And this is just another way of writing this. If you multiply here, you will find that this is the same formula. So we've talked about correlation, and we're going to define the Pearson correlation coefficient, which looks at linear correlation, and this correlation coefficient between two quantitative random variables x and y is equal to cov xy divided by standard deviation of x times standard deviation of y. And so standard deviation of x is obtained by taking the square root of the variance here. Okay, so covariance xy divided by standard deviation of x, standard deviation of y. And so you can see that it doesn't make any difference whether you say covariance of y and x or x and y. They'll be the same formula. So what do we need to remember? And so if you have a population of individuals, the linear correlation coefficient between x and y is given by that. And if you only have a sample of n, which is sampled from a population, and you want to estimate the correlation coefficient given by the sample, then you use this formula, which is slightly different, just like with variances. And so you can see in this formula, in this way of writing the formula, that we have sum of xy minus n times the product of the means divided by the standard deviation. So this is a measure of the strength of the association between x and y, and you can see there's a sort of standardization, subtract the mean and divide by the standard deviation. And so this leads to the properties of the correlation coefficient. Correlation coefficient is always between -1 and 1, and the closer rho is to 1 or -1, the stronger the linear association. If rho is close to 1, it means that when x increases, y increases. If rho is close to -1, it means when x increases, y decreases. So rho is independent of the units, so centimeters, whatever, kilograms, whatever. It has no unit, because you can see here that we have, if x and y are, say, x is centimeters, y is kilos, this is also centimeters, kilos, and divided by centimeters, kilos, so it has no unit. And if x and y are independent variables, then rho is equal to 0, but be careful, rho equals 0 does not mean that x and y are independent, because there may be some other type of association which is not linear, because this correlation coefficient only examines linearity. And so here, obviously, if you're looking at estimations, then it's the same properties as for the rho. So this is to illustrate why I say that this is to illustrate this, that when rho is close to 0, it doesn't mean that the variables are independent. So here, if rho equals 0, you kind of expect, if there's no relationship, this is basically what you would expect, just kind of a random block with when x increases, you don't really know what happens with y. But here you see that the four graphs have almost 0 as linear correlation. But in these 4 cases, there are very different case scenarios which we can observe. If you looked at this graph, what can you see? What happens when x increases? When x increases, y is still, on average, equal to 2. It looks like nothing's happening, okay? If you just look at the mean. But if you look at the variability, you can see that when x increases, what happens to y? It becomes more and more, the variance of y is greater and greater, okay? So there definitely is something happening, but it's not in terms of the mean, okay? Y is constant, y is on average equal to 2, en moyenne, mais la variabilité augmente. And here, you can see that if you look at all the colors, all the points together, it also is not very clear what is happening. When x increases, something strange happens. But if you looked at the 2 subgroups here, So for instance, maybe this is men and women mixed together, but if you notice there's some kind of strange thing happening, it might be that this is men and this is women, and in that case, you can see two very strong tendencies which are not apparent if you mix everything together. And this is an important example which shows you that even if the linear correlation is 0, you might have a non-linear correlation, okay? And so you mustn't dismiss association between the variables. And this is the opposite, where we have a very strong correlation of close to 1. Here is what we expect to see, but here you see that if you look at the data, there's a strong correlation, but actually most of the data doesn't seem very correlated, and it just has 1 point over there. And if you exclude that point, because you see it's extreme, then you realize that actually the correlation is much lower, okay? So correlation is very sensitive to extremes. So the next thing we can look at is that there's a test of significance of the correlation coefficient, where H0 is that there's no linear correlation, and you can test whether there's a significant linear correlation using this test statistic, which is it follows the student distribution, which is why it's a T, and you take the, so this is the real linear correlation coefficient, rho, like when you have mu and m, and this is R, the estimate of the real correlation coefficient. And so you just calculate R over square root of 1 minus R squared over n minus 2, where n is the number of the size of the sample. And you need to assume that the distribution of y is normal and of constant variance for each value of x. And then you can reject the null hypothesis of no significant correlation if your test statistic is greater than the threshold value, as usual for a test, or if p-value is less than alpha. So for instance, here with our example of diastolic and systolic blood pressure, then R equals 0.8 nearly. If you calculate the test statistic, it's 7.82, which is much greater than 2. So we reject the null hypothesis, and there is a significant linear correlation between systolic and diastolic blood pressure. So that's to show the threshold value of around 2 here. So here, this is an important point concerning correlation. Make sure you do not confuse correlation and causality, okay? So, for instance, I ask all my students what they had for lunch just before their exams. And over the years, I measured the quantity of chips, French fries, that they eat before the exams. And I've noticed there is a very strong correlation. The more chips, that's the English word, or fries is the frites, okay? The more chips they've eaten, the better their results in the exam. So that's a correlation, okay? Do you think that you should then deduce that you should eat lots of chips to get good marks at the exam? No. Okay, I don't recommend it. So that's an example of confusing correlation and causality. And there it makes you smile, but you know, COVID and everything, something happens and there's a correlation between one and the other. So we necessarily think that because there's a correlation, A causes B. Okay, so that's something you have to be very careful of. So that's a little cartoon. I used to think correlation implied causation. Then I took a statistics class, now I don't. So then the other one says, sounds like the class helped, maybe. So you see, she didn't, but she believed he believed correlation implied causation. Then he takes the statistics class, now he doesn't. So is it because of the stats class? Yes or no, so it's just a little statistician humor, anyway. So remember, correlation doesn't imply causality. Remember that you can have an association, even if R is equal to 0, it might mean that there is not a linear association, but there might be a non-linear association. Okay, so you have to be careful of that. And you also have to be careful of not basing your data on means. So what does that mean? What does that mean? I'm just going to check. Okay. This seems to be in French. I think I had another book. Yeah, so what does the green mean? Data based on means. I'm going to explain what that means. So if you have, say, you're looking at the relationship between weight and height, okay, in women, and you have 4 groups of women, or 4 groups of 10 women, okay? So altogether you have n equals 40 women, and you have 4 groups of 10 women. And you think, so if you look at all the data, you're going to get something like this, okay, 40 points, okay? But someone says, oh, I can't be bothered doing the study and calculating the correlation coefficient for the 40 women. I'm just going to take the means, the mean weight and the mean height for each group, okay? So I have 4 groups and I can calculate the mean weight and the mean height. So then I would just get 4 points, maybe like this. Okay, instead of having 40 points, I would just have 4 points, yeah? So then if I just calculate the correlation for these 4 points, because there is much less, so maybe I shouldn't put that, I should put more like this. Say this isn't there, okay? But basically, there is less variability. So the correlation in the blue group is going to be, say, I don't know, 0.7. And the correlation in the red group, because there's only 4 points, it will be much higher, okay? Because there's less variability. So it's wrong, it's not right to do that. You mustn't base your data on means because it will artificially increase the value of the correlation because you're reducing the variability because there's less points, okay? Vous avez compris ça en français ou je le répète?
Que vous pouvez répéter.
Je viens de le dire. Au moins, vous en fichez pas. Donc, c'est peut-être pas le cas de tout le monde ici. Alors, ici, je dis que si, vous avez compris ça ou pas? Il y a 40 femmes et on s'intéresse à la corrélation entre le poids et la taille, par exemple. D'accord? Si on se base sur les 40 femmes avec leur poids et leur taille et qu'on fait le graphique et qu'on fait le coefficient de corrélation, c'est très bien. Si on se dit, il y avait 4 groupes de femmes, parce qu'admettons, je ne sais pas, on est allé dans 4 cliniques différentes ou quelque chose comme ça, 4 groupes de 10 femmes, et on se dit, bah, moi, ça m'embête de faire les calculs sur les 40, je vais juste prendre la moyenne du groupe 1, enfin, la valeur moyenne de la taille du groupe 1 et le poids moyen du groupe 1, pareil dans les 4 groupes. Vous voyez ce que je veux dire? Du coup, on a finalement que 4 binômes, poids, taille. Vous voyez ce que je veux dire? J'ai que 4 points à mettre sur mon graphique. Du coup, en fait, je vais me retrouver avec beaucoup moins de variabilité. Vous voyez, de fait, je ne vais pas avoir, par exemple, si ce point-là, c'est la moyenne de 10 points qui sont comme ça,
oui.
Ben, du coup, artificiellement, j'ai réduit la variabilité. Ce qui fait que quand, alors vous pourriez le regarder avec les formules, mais en gros, quand on va calculer le coefficient de corrélation, il va forcément être beaucoup plus important que celui-là, parce que par exemple, vous vous souvenez, dans le coefficient de corrélation, on divise par la variance. Et là, la variance des 4 points, elle va être beaucoup plus faible que la variance des 40 points. D'accord? Puisque vous avez déjà fait une moyenne, en fait. Et donc, ce que je dis là, c'est que faites attention de ne pas vous baser sur des moyennes, mais de bien prendre tous les points, si jamais il y a des moyennes. Donc, c'est un cas de figure comme ça qui peut arriver. Et dernier point, et on arrêtera pour la corrélation pour aujourd'hui. Correlation depends on the range of measured values, which means, alors là c'est pareil, the greater the range, the greater the correlation. D'accord? Plus vous avez, c'est comme ce qu'on avait là tout à l'heure, ici. If you look at this, okay, when you increase the range, you increase the correlation coefficient. So you have to be aware of the fact that this makes a difference, okay? The greater the range, the greater the correlation. Voilà. Correlation depends on the range of measured values. Okay, so I'm going to write down where we got to today, so I know where we are next time, and we can stop for today. Thank you very much. Okay, bye on Zoom. See you next time.